All right, let's take a look at first bad version from the Grind75 question list. You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n versions from 1 to n, and you want to find out the first bad one, which causes all of the following ones to be bad. You're given an API, bool is bad version given some version, which returns whether the version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. So the example they give you, n is equal to 5, and the first bad version is 4. You're going to output 4. Same with the example 2. If you've only got one bad version, you're going to return 1. The constraints are such that bad and n are going to be between 1 and some giant positive number. All right, let's look at the explanation to see how we can tackle this one. So this first bad version question is really a modified binary search problem. You might have guessed that. And so the way that we're going to solve this is by making the same kind of decisions, but what we do is going to be a little bit different because we're not looking for a specific value. We're looking for the first bad version. So in this example, I've got 1 to 7, and 5 is the first bad version in this case, and so is 6. 6 is also a bad version, and 7 is also a bad version, but 5 is the first bad version. So how we're going to do this is within our binary search, which is of course going to be defined as in a loop between while L is less than or equal to R. We're going to do this loop. That's an R, by the way. And we're going to calculate the midpoint. So M is going to equal to, in this particular case, it's going to equal to 4. And then we're going to ask the question, is this value 4, is this a good version or a bad version? If it's a good version, what does that tell us? So we look at 4, yes, it's a good version. So what that tells us is we need to contract our left pointer. So we're going to say L is equal to M plus 1. So we're going to take our L here, and then we're going to erase these from consideration. The range that we're going to look at is going to be between the 5 and the 7. The next time we do that, M is going to equal to 6. And when we look at the 6 here, we can see that it is a bad version. So what does that tell us? Well, that tells us that the bad version that we need to store, the first bad version that we need to store initially, is going to be this one, right? So we're going to store bad version. And that's going to be a variable that's like outside the loop. And what that tells us is we also want to contract the window to the, we're going to move our right pointer to the left. So that what that means is R is going to equal to M minus 1. And what that means is we're going to get to the situation where the right and the left pointer are both pointing to the 5 here. And because our loop is less than or equal to R, it's going to exhaustively look at both values. M is going to be the same value as the 5. And then finally, it's going to hit this loop again, and we're going to say M is going to equal to 5, and this is a 5. We're going to store the bad version because it's an earlier bad version, so we'll store bad version. And that's the end of our loop. And at the end of this, we just return the bad version. That's what that says. All right, so in terms of a time complexity, the time complexity is going to be O of log n, where n is the number of versions that we have, and the space complexity is going to be O of 1 because we're not storing any input that scales, or we're not storing any space that scales with the input. So to start this problem, we want to declare our left and right pointers. I'm going to declare it in a tuple initialization to make it a little bit tighter. And n doesn't start from 0 in this problem. It starts from 1 actually, and it goes all the way to n. And what we're going to do, we know at some point we're going to have an L less than or equal to R, which is your traditional binary search type loop. But we also need to store the first bad version, and we'll set it up to start at n because we know that the last version is going to be a bad version. And at the end of this loop, we're going to return our first bad version. All right. Our M is going to be equal to L plus right minus left divided by 2 to prevent integer overflow. And then we're going to do our check here. So we're going to say if is bad version M, do one thing, otherwise do another thing. So remember, if we get something and it gives us a bad version, what that means is we want to store our first bad version as M. I can type here. And then we also want to contract our pointer to say right is equal to m minus 1, because it could be that there's an earlier version that is the first bad version. This is just the first bad version that we've found so far. Otherwise, if it's not a bad version, what that tells us is the first bad version must be somewhere more to the right. So we're going to take our left pointer and we're going to say that's equal to m plus 1. And I believe that should be all the code. I'll run it real quick just to see if there's a problem here, and that seems to work the way I expected. And now we're going to submit it. And there you go. Hope you enjoyed this video.